Welcome to the Deep Dive, where we take your stack of sources and build instant expertise. Today, we are going right to the absolute bedrock of physical reality. We're talking about chemistry. It's the study of matter, the material stuff of the universe and all the changes it goes through. But we aren't just defining matter. Our mission today is to connect what you actually observe, the big macroscopic stuff, the color of a substance, its melting point, whether it dissolves, and link that directly to the unseen microscopic architecture of its atoms. We're going to figure out how that structure governs everything.
And if you connect this to the bigger picture, this is where that foundational knowledge just pays off huge dividends. We're essentially learning the language of the physical world, understanding how that structure works, right down to the actual geometry of the molecules. That's what lets engineers pick the right materials, or pharmaceutical companies design a drug that fits into a receptor just like a key in a lock. We're really starting from the ground up to understand why things behave the way they do.
Okay, let's unpack this blueprint then. Starting with the basics. Classification. What is all the stuff around us? Well, everything in the universe that has mass and takes up space, it falls into one of two big categories. You've got pure substances and you've got mixtures. And it's all about the composition. A pure substance, like, say, table sugar or carbon dioxide, it has a definite and constant composition. Right. You can always write down a single, unvarying chemical formula for it. But a mixture, that's just a physical mashup of two or more pure substances. And the critical word here is variable composition.
Variable, yeah.
Think about air. It's mostly nitrogen and oxygen, sure. But the amount of water vapor, the humidity, or argon, that changes all the time, depending on where you are.
And when we drill down into that pure side, we hit the ultimate building blocks. Elements and compounds. Elements, like oxygen or gold, they're the fundamental substances. They're made of only one kind of atom. A compound, then, takes those elements and combines them chemically. But, and this is key, in a fixed specific ratio. And the properties of that new compound are, well, they're profoundly different from the elements that formed it.
Completely different.
Yeah. I mean, water, H2O, is the perfect example. You have two highly flammable hydrogen atoms and one highly reactive oxygen atom. And they combine to create this stable liquid that we use to put out fires. The chemical change just destroys the original properties.
That fixed ratio is everything. So going back to mixtures then, they're much less rigid. We have two flavors, right? Homogeneous mixtures are uniform all the way through. You can't see the different parts, even though they aren't chemically bonded. Like vinegar or a perfectly mixed cup of tea. People call them solutions.
And the other type, heterogeneous mixtures, where the composition is clearly not uniform. Oil and water is the classic one. Or, a bowl of cereal, you can easily see the parts. And what's really insightful here is what this all means for separating them.
Okay, so if I have a compound, let's say rust iron oxide, how do I get the pure iron back out of that?
You have to use a chemical reaction. You have to break those incredibly strong fixed chemical bonds. And that usually takes a lot of energy or very specific conditions. It's a fundamental change to the substance itself. But if you just want to separate a simple mixture, say salt dissolved in water, you only need physical means. You just boil the water off. That's distillation.
Okay.
Or use a filter or chromatography. You're just physically moving the molecules apart without changing their chemical structure at all. And that's a huge difference between the two categories.
So now that we know what stuff is, how do we describe it?
Right.
We use properties, and those break down into physical and chemical. Physical properties are characteristics we can measure without changing what the stuff is. Color, volume, mass, electrical conductivity. That's just copper being copper. Chemical properties, though, describe its potential for change, its ability to react and form a whole new substance. Flammability, toxicity, or how easily a metal rusts. These are all latent capabilities.
And this brings us to a really crucial distinction, which is extensive versus intensive physical properties. This is where you get real insight into how to identify things. Extensive properties are pretty straightforward. They depend directly on the amount of material you have.
Okay.
Mass, volume, length, the total amount of energy.
Right.
If you double the size of your sample, you double these properties. They're additive.
Right. But if we want to identify some unknown material, we can't really use its mass, because if I just give you more of it, the mass changes. We need the intensive properties.
Exactly.
These are the true intrinsic characteristics, the fingerprints of the substance, because they are independent of the amount. Color, melting point, boiling point, pressure, and density. So if I had a tiny gold nugget and a massive gold ingot, their color, their melting point, their density, all identical. That constancy is the key. But why?
That is the critical question. If you combine two identical systems, the temperature doesn't double, right? It stays the same. The melting point stays the same. The ratio of the parts to the whole is fixed. And that brings us to the most insightful, intensive property of all, density.
The density moment. Density is the ratio of mass to volume.
Precisely. Mass and volume are both classic extensive properties. They both change with the amount of stuff. But when you divide one extensive property by another one, the dependence on the quantity just cancels out.
Oh, I see.
And you're left with a fundamental intensive property.
So we're hunting for these intrinsic fingerprints. If you have pure water, its density is about 0.998 grams per centimeter cubed at a certain temperature. And that value never changes, whether you have a teaspoon or a swimming pool.
Right.
That ratio is what tells us if something will float or sink. It's why corn oil with a lower density always floats on water. It just has a lower mass concentration in the same amount of space. So here's a little mnemonic to help you remember it. Intensive stays independent. Extensive expands with size. Okay, so moving from static properties to dynamic changes. If we apply energy to matter, we get a change. And again, it's either physical or chemical. A physical change affects the state or appearance, but not the internal composition. Melting ice to water or boiling water to steam, it's still H2O. No bonds are broken or formed.
A chemical change is where the real magic happens and new substances are formed. You break the existing bonds and you rearrange the atoms into something totally new with entirely different properties. When you burn natural gas, which is methane, CH4, you mix it with oxygen. The chemical change gives you carbon dioxide and water vapor. You can't get the methane back just by cooling it down.
There's one cool physical change to remember: sublimation. It bypasses the liquid state completely. Dry ice is the classic example, right? Solid carbon dioxide just goes straight to a gas. It's still CO2, just in a different physical form.
Now, all of these changes, physical or chemical, they all involve energy. And we usually categorize energy as either kinetic, that's energy of motion, or potential, which is stored energy. For chemistry, the most vital potential energy is the energy that's stored right inside the chemical bonds themselves.
And understanding that potential energy, that's how we talk about chemical changes being exothermic or endothermic, isn't it?
Precisely. If a reaction is exothermic, it releases heat. It means the products have less potential energy stored in their bonds than the reactants did. So energy was released, usually as heat, out into the surroundings. And conversely, endothermic means the products have more potential energy than the reactants. So the reaction had to suck in heat energy from the surroundings to make that happen. And finally, we should probably clarify the difference between heat and temperature. It's a classic point of confusion.
Yeah, people use them interchangeably.
They do. Temperature measures the average kinetic energy of the particles in a substance. It's a measure of intensity, how fast they're all giggling around.
And heat. Heat is the total amount of energy that transfers because of a temperature difference. So, for example, a tiny cup of scalding hot coffee has a very high temperature. Its molecules are vibrating really, really fast.
But a giant swimming pool, even if it feels cool to you, contains exponentially more total heat energy. It just has vastly more molecules, even though their average kinetic energy, their temperature, is much lower than the coffee.
I see.
Heat is the total energy transfer. Temperature is just the particle intensity.
All right, now I get to the control room. The microscopic world of bonds and shape. How the atoms link up determines everything about those bulk properties we just talked about. And we have two main types of chemical glue. First, ionic bonds. These are attractions between fully charged ions. So you have metals giving up electrons to become positive cations, and non-metals accepting them to become negative anions. They just stick together like tiny, powerful magnets.
And second, you have covalent bonds. These are typically between non-metallic atoms, and they form by sharing electrons. Now, this sharing can be equal, which makes a nonpolar bond, or it can be unequal. We call that a polar covalent bond, where one atom basically hogs the electrons more strongly, creating partial positive and negative charges across the bond.
Which raises a really important question. We can draw these bonds on a flat piece of paper, but molecules exist in 3D space. So how does that 2D drawing predict the actual 3D shape, the molecular geometry?
This is where we use this beautiful, simple principle. It's called valence shell electron pair repulsion theory, or VSEPR. The rule is actually deceptively simple. Every electron group, whether it's a single bond, a multiple bond, or a lone pair of unshared electrons, they're all negatively charged. And so they all repel each other. So for a molecule to be as stable as possible, these electron groups have to arrange themselves as far apart as they can get in three-dimensional space. Think of it like tying balloons together at the center. They naturally push into specific shapes to maximize the distance between them.
So if the central atom only has 2 electron groups, the balloons just push each other as far apart as possible, 180 degrees, and that creates a linear shape like carbon dioxide, CO2.
Exactly. Or if there are 3 groups, they spread out in a flat plane at 120 degrees. That's trigonal-planar. But the most common, and maybe the most important shape for life, is when the central atom has 4 electron groups. They can't stay flat. They're forced into a 3-dimensional tetrahedral arrangement, spacing themselves at about 109.5 degrees.
Carbon tetrachloride, CCl4, is a perfect tetrahedral example. But here's the profound contrast that controls everything. Solubility, boiling points. The difference between CO2 and H2O.
Right, CO2 is linear. It only has 2 double-bond electron groups, so the atoms are 180 degrees apart. It's a nonpolar molecule. But water, H2O, also has 4 groups around the central oxygen. But, and this is the whole story, 2 of those are lone pairs. Yeah. And those lone pairs repel the bonding pairs much more strongly than other bonding pairs do.
So they act like big, invisible bullies, just pushing the 2 hydrogen atoms closer together.
Exactly that. This distortion forces the molecule into a bent shape, and it drops the angle to just below that perfect 109.5. That bent shape is why water is extremely polar.
Yeah.
And that polarity determines its ability to dissolve almost everything, its surface tension. It supports all known life.
Wow.
The shape truly dictates the function. If water were linear like CO2, the world as we know it, it just wouldn't exist.
That is the ultimate synthesis then. We've gone from classifying a material as a mixture or a pure substance to identifying it using intensive properties like density and finally showing how its fundamental 3D architecture driven by electron repulsion dictates whether it's going to be a gas, a liquid, or a key component of a cell. So to quickly recap the journey, remember that classification system. It determines how you separate matter. Focus on those intensive properties, the independent identifiers that stay constant no matter the sample size. And never forget that the unseen molecular geometry is the ultimate control factor for a molecule's behavior.
And for a final provocative thought for you to chew on.
Yeah.
We relied very heavily today on the constancy of intensive properties, the idea that doubling your system doesn't change its temperature or its pressure. And this rule holds true for everything you see and touch. However, when scientists study nanosystems, systems measured in billionths of a meter, this rule starts to completely break down. Yeah. When you combine 2 extremely small identical systems, the resulting intensive properties like temperature and pressure can actually increase. This happens because the surface area becomes so huge relative to the volume that interactions we normally ignore become dominant, and they essentially convert external stored energy into internal motion. It just shows that the fundamental rules of matter, which we rely on for the bulk world, are constantly being tested and refined as we explore matter at its absolute smallest scale.